Hi, my name is Bree, and I'm working alongside Nathan, Morgan, Shannon, and Nico on the Assessing Intrinsic Foot Muscle Strength capstone team. There are many different muscles in your feet, controlling your actions from walking, running, agility, and even balance. The intrinsic foot muscles are a specific group of muscles responsible for the coordination and agility of individuals. Not much is known about the IFMs, especially when it comes to categorizing whether they're weak or strong.
People with weak intrinsic foot muscles typically face lower leg pain, foot cramps, and poor balance that could lead to the decreased self-independence. The goal of the project is to find a way to accurately measure the intrinsic foot muscle strength so that we can help improve the individual's quality of life.
To further understand the project, you must first understand a little bit more about the function of the foot as well as its anatomy. There are two movements of the toe that our group is focused on. Abduction, or the spreading of the toes, is depicted on the left, and adduction, or the clenching of the toes, is depicted on the right. As for the anatomy, the foot contains 4 layers of intrinsic foot muscles, also referred to as IFMs. IFMs are muscles that start and end both in the foot. For our project, we are mainly focused on layers 1, 3, and 4. Here is the first layer, which it starts at the top of the foot, and it is responsible for the abduction of the big and pinky toes. Moving down one layer, the second layer does not contribute to the abduction or adduction of any of the toes, which is why this is the only layer we are not specifically focused on. Going deeper, the third layer, pictured here, is responsible for the adduction of the big toe. Finally, the deepest layer, the fourth layer, is responsible for the adduction of the 4 little toes.
Intrinsic foot muscles can weaken with age and can be a common problem in elderly. Weak intrinsic foot muscles also associated with diabetics who experience nerve damage in their feet. Weak IFMs can progress into more serious conditions such as muscle dystrophy. This is why it is important for our group to create a prototype that can enable professionals to measure, monitor, and make diagnosis of the feet. With known IFM exercises, individuals can perform these tasks at home to strengthen the IFMs. This can help stabilize or improve their condition. Our team was lucky enough to inherit a previous independent research study. Since then, we have been working closely with a biology department in order to create an apparatus that will allow the researcher to accurately measure the forces of the intrinsic foot muscles using foot immobilization and force sensors. We have fabricated an alpha prototype that is currently being tested by the team. Unfortunately, due to COVID, our team has been unable to conduct a full human study.
Here we have our alpha prototype for our housing subsystem. The housing prototype places a user's foot in plantar flexion as shown. For most, that is between 30 and 50 degrees, although it varies based on many factors such as flexibility. When the foot is placed in plantar flexion, the extrinsic foot muscles are stretched and then are unable to contribute any forces during the test. Using the adjustable housing, we are able to accommodate a variety of individuals and ensure comfort to the participant by preventing strain.
The angle for testing is determined by finding the largest angle between 20 and 50 degrees, also known as plantar flexion, that does not cause the individual being tested discomfort. This angle prevents the extrinsic foot muscles from engaging, stretching them out, and allowing the device to accurately isolate the intrinsic foot muscles. With the current apparatus, we only have the ability to accurately measure the big toe and little toe's abduction. In order to accurately measure other forces, we need to integrate a new concept into our existing housing device. The design we are currently moving forward with looks like this. It is a rigid U-shaped piece that can be slid between the toes and then pressed against to measure the abduction and adduction, and also prevent neighboring toes from adding to the force of measurement. Another area we are seeking to improve is to further immobilizing the foot by adding straps around the ankle and to the top of the foot. This will restrict the foot from being able to lift off the housing, which can result in some skewed data.
Once the user's plantar flexion angle has been determined and the housing has been adjusted, for this individual here it's about 45 degrees, the testing can begin. As explained before, plantar flexion minimizes the influence of the extrinsic foot muscles. Utilizing our single tag pressure sensor, we are able to capture data through our Arduino Uno. As Shannon previously mentioned, we are moving forward from concept generation stage with a design that can be slid between the toes like so, and then we can add our sensor on either side of the toe to then measure the abduction or adduction force.
Based on data that we received from the previous research study, as well as the data we collected ourselves, we decided to utilize a single-tack pressure sensor connected to an Arduino Uno for data collection. By pressing down on the single-tack, we were able to collect an analog reading that we can convert into a force. It is important to determine the placement of the sensor in correlation to the housing and toes, because that will provide the most accurate results without causing the user discomfort.
As Nico said earlier, the sensor collects instantaneous force outputs from the toes, which are able to read and analyze through an Arduino board. The Arduino code translates the force outputs into an equivalent voltage so that we can read and understand the data better. Before testing the sensing system on our feet, we first performed tests in order to verify the code and ensure everything was appropriately calibrated. The testing on our team members seeks to validate that the apparatus will provide accurate, repeatable data that makes sense in terms of our project.
The team works diligently to ensure that the housing remains both comfortable and safe for all individuals testing with it. We have done so by conducting failure analysis at various stages of the project, then working to identify the best ways to eliminate or mitigate these potential failures. In addition, the team has drafted a detailed procedure that has allowed us to continue to test on ourselves through these unusual times. We hope that at the beginning of this next semester, we are able to get our procedure approved and begin a broader human trial.
The end goal of our capstone is to create an apparatus that will precisely and accurately measure the IFM muscles. With this data, we will be able to determine what a weak and strong IFM muscle data range will look like and further help patients. From this information, we can then apply strengthening exercises and physical therapy to patients with weak IFMs. Doing so can improve quality of life and increase independence of each individual.
Thank you for taking the time to watch this video and learn more about our capstone efforts. We look forward to answering any questions that you may have about our capstone project.